Welcome to the second last video on mathematical formulations of microbial growth and the second class on microbial kinetics. Today, after a quick recap of the take-home messages from the last class, we will discuss together the concept of growth-limiting compound, to then move and discuss a generalized method based on bioenergetic grounds that allows us to estimate the parameters to finally characterize any growth system also from a kinetic perspective. I will then conclude the video with an outlook on how all what you learned so far can be used to model and characterize more complex ecosystems where multiple metabolisms coexist, and how as engineers we can use the numbers we derive to define the conditions under which, for a given biological system, the metabolism of interest will prevail. Now, let's start with the two take-home messages from the previous class. First, we learned that even for thermodynamically feasible reactions, where products have a lower potential energy than the reactants, and thus the driving force, the delta G of the reaction is negative, so it is defined as spontaneous. Actually, these reactions do not occur spontaneously unless there is an energy input from the outside. We used some highlights from the transition state theory to gain a conceptual understanding of what this energy that we call activation energy or delta G double dagger is. So according to this theory, or this theory hypothesized that in the transition from the reactants to the products, all these unstable intermediates, there is one that has the maximum difference in potential energy with the reactants. To reach this transition state, we need to provide at least this required energy difference. So this is what the activation energy is. We also reflected on the fact that the existence of an activation energy for basically any reaction is what allows us to store safely the food and then burn it whenever we need during the winter, as long as we have a lighter or a spark to provide this initial activation energy. Following the same theory, we also developed or derived a rate expression that allowed us to relate the rate of a reaction with the activation energy, as well as with the temperature. We saw that according to this reaction, to this equation, the rate increases for decreasing activation energies and vice versa. And the rate increases at higher temperatures and decreases when the temperature is decreased. In the perspective of the activation energy, we also acknowledge the very essential role of enzymes in allowing reactions, in lowering the activation energy and allowing reactions 6 to 12 orders of magnitude faster at ambient temperature and pressure as compared to the same reactions in the absence of enzymes. And this is the very reason why life can exist on Earth. And before moving to the other take-home message of the previous class, regarding this, I would like to highlight something that I felt was not sufficiently stressed. It's the fact that enzymes really play a significant role by allowing at mild conditions reactions to occur. So this is very important. All at ambient or around ambient temperature and pressure is where enzymes make the huge difference. And the second point, I felt that I was a little bit rushed, is that when we discussed the rate equation, of course we focused on the rate constant, where all the dependencies come into play, but we lumped together the concentration of the reactants. So more correctly, to reflect the experimental evidence that we have, we usually express the rate as a function of the concentration of the reactants, the product of their concentrations or activities, each of them for reactant I to the power Ni, where Ni is actually what defines the order of the reaction for reactant I, and usually but not always coincides with the stoichiometry of the reaction. Now, said so, let's go to the second take-home message of the previous class. We used the Herbert-Pert equation, or we introduced the Herbert-Pert equation to discuss the dual use of substrate in microbial metabolism. Experimentally, it is observed that at higher growth rate, the yield increases. And the reason for this is that the substrate that is consumed, and is actually what we measure experimentally, is used both for maintenance and growth. And this is what the Herbert-Pert equation expresses. The biomass-specific per mole X substrate or electron donor consumption rate is distributed among the metabolism, which is what we derived in terms of stoichiometry with the Gibbs dissipation energy method, and the maintenance, which is in essence the catabolism, which are processes that consume energy generated by the catabolism but do not lead to biomass production. And then, okay, scaled by their corresponding stoichiometric coefficients, where this is from the catabolism, and this is the inverse of the biomass growth yield, the maximum one that we derived with the energy Gibbs dissipation method. We rearrange the same equation with terms that are more commonly used, such as mu for Qx for the biomass-specific biomass production rate, and m for the maintenance, for the biomass-specific substrate consumption rate for maintenance processes. We also used a graphical representation of this equation, where this equation here is linear. If we plot Qs, the substrate biomass-specific substrate consumption rate, as a function of the biomass-specific growth rate mu, and the intercept becomes the maintenance coefficient. In other words, the full substrate consumption rate that we measure in the absence of growth is only for maintenance purposes. If we look at the same from another perspective, we can also graph this biomass-specific substrate consumption rate for maintenance over the overall biomass-specific substrate consumption rate. And if we look at the extremes, we see that at very high biomass growth rates, the maintenance contribution to the overall substrate consumption is very minimal. Whereas when growth rate is very low, most of the substrate consumed is used for maintenance purposes. Now, to look at the same and discuss from a yield perspective, we also rearrange this equation here to obtain an equation that expresses the experimentally observed biomass yield as a function of the maximum biomass yield and the experimental conditions. If we look at it graphically, we see that the experimental yield is not a constant, but depends on the mu. At high mu, it gets closer and closer to the maximum biomass yield. Whereas at very low growth rates, Most of the substrate is consumed for maintenance, therefore the yield on substrate consumption is very low. And this concludes this recap of take-home messages, and let's start with the real topic of this class. In other words, saturation kinetics. To discuss about saturation kinetics, we need to go back to stoichiometry. Now, a stoichiometric equation allows us to relate with mass balances all the elements in an equation, in a reaction. For example, in the metabolic reaction, all stoichiometric parameters are expressed, or we conventionally express them, per mole biomass produced. So we know how much ammonia, how much acetate, and so forth are consumed to produce 1 mole of biomass. Now let's assume a situation in which all substrates are available in stoichiometric proportions except one that is available in lower concentrations, relative concentrations compared to the others. This becomes the growth limiting substrate. As a matter of fact, we can produce only an amount of biomass proportional to this growth limiting substrate. And the amount of all the other substrate that we will consume to produce this biomass will be proportional to this growth limiting substrate. So we will have an excess, remaining excess of the others. Now what we learned, or based on experimental evidence, is the fact that kinetically, the consumption rate of the growth limiting substrate depends on its actual concentration in the bulk. And this is exactly what we expressed with saturation kinetics, or Monod-like equations. A Monod-like equation is expressed in this form, where for J being the single growth limiting substrate, in other words, as we said, all substrates are in excess and there is only one substrate that is proportionally lower, is consumed as a function of the maximum biomass specific growth limiting substrate consumption rate multiplied by this switching function, which depends on the concentration of the substrate and half saturation constant. Now I hope that this will get clearer in a couple of slides. However, let's define the terms that are involved in this equation, because these are the terms we will focus on in the generalized method that we will develop later on. So the maximum biomass specific consumption rate of the growth limiting substrate, J, or actually compound, it can also be a nutrient, for example, and the affinity constant for the growth limiting compound expressed in terms of with units of a concentration to make it consistent here. Now, if we graph this equation here, it looks like this. The substrate, the biomass specific consumption rate of the growth limiting substrate as a function of the concentration of the growth limiting substrate has this shape here, where it tends to QS max for concentrations that are infinite or towards very high, where this term tends to 1. However, at lower concentrations, this term starts to play a significant role in decreasing the substrate consumption rate compared to the maximum one. And this is called also half saturation constant, because it's the value of the concentration at which the substrate consumption rate is halved. Now, with this in mind, and do not worry if now it sounds a little bit still abstract, because we will work on it extensively. Now we can at least summarize what we learned so far. So, the Herbert-Pert and the Monod-like equation allow us to define kinetically a whole system. So, the Herbert-Pert equation states that the biomass-specific consumption or transformation rate of any soluble or particulate compound, I, is a function of the growth and the maintenance. Basically, the flux is distributed between growth and maintenance. For this single growth limiting substrate J, the biomass-specific consumption rate is proportional to the concentration of the specific substrate and the maximum consumption rate of the same substrate. By definition, as we said, we always used consistently throughout these classes, all the rates are positive as well as the stoichiometric yields. Now, in summary, I hope this will be clear, especially at the end of the final exercise where we will bring everything together, is that we only require 4 parameters. One is the stoichiometric parameter and 3 kinetic parameters to fully describe a growth system. Now again, let me summarize this. We have a growth yield of biomass growth on any substrate or product I with the Gibbs free energy dissipation method. We have a maintenance coefficient which tells us the moles of electron donor, in this case, consumed per mole biomass per hour to maintain the complexity of the cell. We have a QJ max, the maximum biomass specific growth limiting substrate consumption rate, and the K, which is the affinity constant for the growth limiting substrate J, which tells us at which concentration the rate of consumption of this substrate will be half of its maximum. In the next part of this video, we will learn how on thermodynamic grounds or bioenergetic grounds we can estimate at least these 2 parameters to finally derive and describe a full system. And with this, we start the parameters generalization section. In analogy to the Gibbs free energy dissipation method that allowed us to estimate or gain a first approximation for the maximum biomass yield on substrate, also here actually the same authors looked into a very big inventory of experimental data, looking for common traits between very distant metabolisms, from aerobic respiration to fermentation with organic or inorganic substrates at different temperatures. And the first very interesting observation was that the energy requirements for maintenance seem to be a constant across all these distant metabolisms. What we refer to is the biomass-specific Gibbs energy consumption for maintenance. And what the authors observed is that this seems to be a fixed number, 4.5 kilojoule per mole biomass per hour at 25 degrees Celsius. And that among all the different variables, the only parameter this value depends on is the temperature. Therefore, there is a temperature correction term, which at first might look intimidating, but I can assure you that you know what it means. When we discussed the transition state theory in our previous class, you learned, or we derived, that the K value, the rate constant, is a function of e to the power of minus activation energy divided by RT, where T is the temperature at which the reaction occurs. Now, if you take a rate constant at temperature general T, like in this case, and you divide it by the rate constant at temperature 298 Kelvin, which is the reference constant, the reference temperature, you can then work on the math, take the logarithm and move on from there, and you will obtain the same expression, which is the reaction rate at a temperature T, in this case this, equals the reaction rate at temperature 298 with e to the power of minus the activation energy divided by R. So this is our activation energy. And even if there are, we can discuss a little bit more in detail, which we will not do here, that the delta G double dagger we discussed has an enthalpy and an entropy term and how they influence the overall correction. But this is what I want you to know, that this is the temperature correction. Now that you have the kilojoule per mole hour of your given reaction, and if you know, and I assume you do, the stoichiometry of your catabolism, we can then obtain the requirements for any compound I involved in the catabolism from this very value, just by dividing it with the delta G of the catabolism and the stoichiometric yield of compound I in the catabolism. As we always assume the fluxes, the rates to be positive, as well as the yields, then there is this minus here because by definition, otherwise would not be a catabolism. The delta G of the catabolism is negative. So then Mi becomes positive. The second observation that the authors made is the fact that there seems to be a physical limitation for the number of electrons that can be transferred per mole biomass per unit time in the catabolism. Now you can think, and the easiest way to understand this is if you think of the electron transport chain, where an electron donor donates electrons which have to go from protein to protein until they are accepted by the final electron acceptor. Now what there seems to be reflected in the collection of experimental data is that there is a limit to the amount of electrons that can be transferred. So for this, what we refer to is this equation here, where the maximum mole of electrons per mole biomass per hour that are transferred is 3 at, again, 298 Kelvin. And then also in this case, it's corrected with an Arrhenius type correction factor, which you should, as we discussed, be able to derive now. Once we know this, we know we can calculate based on the catabolism and the knowledge of how many electrons are transferred. We know the total energy involved, the flux of energy, the kilojoules per mole X per hour in a given reaction, in a given metabolism. And again, as we said, the rates are always positive, and this term here represents the number of carbons multiplied by the number of electrons per carbon mole of electron donor. Once we have this, and this is what we will see in a few slides, we can then use the same Herbert-Pert equation to see how the Gibbs energy distributes among growth and maintenance. But before doing so, I would like to highlight one specific challenge of this approach, which is knowing how many electrons are involved in the catabolism. So if we go back to our candy example, we already know that aerobic glucose respiration involves the transfer of 24 electrons per mole glucose. Now the question is, how many electrons are transferred in glucose fermentation to ethanol? where glucose is both the electron donor and the electron acceptor. Now, to answer this question, we have to have a knowledge of the pathway that is taken to produce glucose, to transform glucose into ethanol and CO2. Now, this is a very schematic representation. And once we know this, we know that 2 NADH are produced here and then consumed. Namely, this corresponds to 4 moles of electrons per mole glucose. What I just want you to realize, and I address you to the references from Robert Clairbaisse and Martin Lostrecht and Seth Heinen for more detailed discussion on how the number of electrons can be calculated. Now, back to the parameters estimation. Where we left was when we wrote the Gibbs energy distribution equation, Herbert-Pert equation. Part goes to growth and part to maintenance. Now, if we rearrange this equation here, we can finally derive the maximum biomass-specific biomass growth rate, mu max, which might ring a bell for some of you, which is simply the expression of what we learned. The 3 mole electron per mole biomass an hour, the 4.5 kilojoule per mole biomass per hour, and here the units are made consistent, and here's the dissipation, Gibbs free energy dissipation, and again the temperature correction term. Once we have now the mu max, we have all the parameters that we need. We can finally express the maximum biomass specific conversion rate of compound I as a function of parameters that we have calculated or derived. The mu max, the maximum biomass growth yield on compound I, and the maintenance. And this is the catabolic coefficient to highlight the fact that yes, it becomes 1 if we refer it to the substrate, but we can also calculate this for any other compound. So to summarize what we have already seen, to describe kinetically a system, we need to understand the substrate distribution among the metabolism with the growth flux, biomass produced per biomass per hour, and the maintenance flux, electron donor consumed per biomass per hour. We also learned that there is one growth limiting compound, the one that, looking at the stoichiometry of the reaction, is limiting, so it's present in relatively low concentrations compared to the requirements for growth and the other compounds. And this, so the rate of consumption of this growth limiting compound is a function of the actual concentration. The Q max that finally we were able to estimate, and the K, which is the affinity constant. Again, all the fluxes are positive and the yields are also positive. And we have now all the perspective. We know how to estimate the maximum growth yield on compound I, the maintenance coefficient, the maximum biomass specific consumption rate of the growth limiting compound, and the only parameter that we are not yet able to estimate is the K. And for this, unfortunately, there is no generalized method, but we have to rely on literature or experimental value. And this leads us to the final small section of this video, which is a recap and an outlook. So in terms of recap and outlook, I would like to go through the procedure of what we learned together so far, and how then this can be used to model more complex communities. So a full description of a microbial growth system. What are the steps that we took and the concepts we learned? So first, microbial metabolism is the sum of anabolism and catabolism. Both anabolism and catabolism are redox reactions. And the catabolism, and this is something I know that you'll learn with David Weisbrod, is the microbial diversity that we observe in the world is coming from catabolism. Whereas the anabolism, as we have seen and we will see with some numeric examples, is very common, is very conserved among different life forms. And so the general framework that we established to estimate the stoichiometry and kinetics of any system requires you to go through these specific steps. Define electron donor, acceptor, carbon source, and nitrogen source. And of course, the composition of the biomass, which will define how much carbon and nitrogen source you need. Based on this, you can derive the anabolic, the electron donor half reaction, electron acceptor half reaction, and the anabolic half reaction, where we have seen that depending on the redox of the carbon and nitrogen source, we might need an electron donor or an acceptor half reaction to be coupled. Based on this, we can derive the catabolic and the anabolic reactions. With the Gibbs free energy dissipation method, we can derive the maximum biomass growth yield on electron donor. Based on this, finally derive the stoichiometry of the metabolism. We can then estimate the substrate requirements, biomass specific, for maintenance, and estimate, after having estimated the mu max, finally the maximum biomass specific consumption rate of the growth limiting compound. And of course, as we said, we need to assume or estimate our K values. Now, what I want to highlight here is the fact that we will go through all these steps for you to consolidate your knowledge in the next and last video, where we will exercise on this. In this outlook, I want to give you a feeling of what we will do next and how we can use all this that we derived to then identify the growth limiting substance J in any given situation. Based on this, establish the mass balance for biomass and the growth limiting compound, and then, depending on the conditions we impose, calculate the concentration and their dynamics of all other compounds. Before doing so, let me have a recap session that is greatly inspired by also the lectures of Robert Clara Basin, where we discuss the implications of all what we learned. So let's compare respiration and fermentation of our candy. What we have seen is that while in terms of anabolism, both metabolisms rely on glucose as carbon source and electron donor. So this is the delta Gibbs free energy change involved in the anabolism, so slightly negative. They also rely on the same electron donor and organic carbon source for the Gibbs free energy dissipation method. So the overall energy consumed in the whole metabolism is the same. Where the two metabolisms differ substantially is in the energy that is released or that can be used from the catabolic reaction. And we see that there is one order of magnitude difference, being it much higher for respiration with oxygen. Simply for the fact that organic carbon is a good electron donor, oxygen is a good electron acceptor. Whereas in fermentation, organic carbon is the donor, good donor, but also a weak acceptor. Based on these values here, we were able to calculate the maximum biomass growth yield on glucose. And this energy difference here is directly reflected in how much biomass can be grown per mole glucose. And of course, this we have seen that for catabolisms that release less energy, there is the need to run the catabolism many more times to produce 1 mole of biomass. This is what we refer to as lambda cat. Now, let's see on the kinetic parameters. If we look at the moles of glucose that are required per mole biomass per hour for maintenance purposes, there is also a huge difference here. Of course, as the energy required per mole biomass per hour we have seen being a constant, irrespective of the metabolism, then of course you need to run less times the catabolism or consume less glucose if the energy released is much higher. So therefore the glucose requirements for maintenance in such a case are significantly lower than in fermentation. Now the opposite is actually true if we look at the number of electrons involved, 24 against 4 moles electrons per mole glucose. Now, as we just learned, there is a physical maximum of electrons that can be transferred per mole biomass and per hour, which is 3. Therefore, the rate at which substrate can be consumed will be much lower for respiration, where many more electrons need to be transferred per unit time than in fermentation, where only 4 electrons per mole glucose are transferred. Therefore, more glucose can be processed per time. Now, if we look at the mu max, now the situation is a little bit different. From the Herbert-Pert equation, we know that Q is distributed, the biomass-specific substrate consumption rate is distributed between growth and maintenance. Now, if we neglect, just for the thinking here, the maintenance, which is reasonable to do as it is comparably very low with respect to Q, we simply obtain that mu max equals the product of the maximum biomass growth yield and the biomass-specific maximum consumption rate. And as we discussed, the yield is higher for respiration, yet due to the fact that many more electrons are transferred per mole glucose, the Qmax will inevitably be lower because we have the 3 moles electrons per mole biomass per hour that limits the electron transport rate. Therefore, as we multiply numbers that go in different directions for the same metabolism, then it's difficult to predict upfront what mu max will look like, or at least how this will compare between these two metabolisms, because it really depends on the value of these 2 parameters that we multiply. Check the numbers when you multiply these parameters, as the yield sometimes is given in the inverse. So really check the numbers. Now, to conclude this, what about the affinity constant? Well, in this case, as we said, we need to rely on experimentally derived yields, whether we derive them our K values, whether we derive them ourselves or we look into literature. And before concluding, I would highlight once again that all these values that we estimate with generalized methods are first approximations. Yet, if we look at the relative error when compared to actual experimentally measured values, the yield is in particularly very low, 10 to 20%. So, as Robert Clairvaux always says, if your experiment gives you a value of the yield of all or of other parameters that significantly differs from what you predicted, then probably you are onto something that is very interesting. And now it's time to understand what will we learn in the last class of this mini course. In the next class, we will build up such a matrix that you should be already familiar in a spreadsheet where we have all our compounds, thermodynamic properties, elemental composition, stoichiometries. We can calculate the metabolic yields based on mass and energy balances, estimate the kinetic parameters now you learned, and then we will start to define influent and boundary conditions to then model and simulate how different metabolisms will coexist under specific conditions when they compete for the same growth limiting substrate, or how they will coexist if they are in a syntrophic relationship. And what we will do is we will explore how you can implement all this in a spreadsheet and then obtain the dynamic simulations, the steady state simulations for chemostats, and we will also very briefly touch upon, while you will have the opportunity to play with it yourself, also sequencing batch reactors. What will we be doing is we will look at a chemostat reactor like this, where we have an influent concentration of compounds I with a flow and a given concentration of biomass, a volume of the reactor, and then we will have the effluent concentration in gaseous form and aqueous form. We will assume for simplicity that they are all dissolved in the liquid. And we will write mass balances in this form, which I assume you are familiar. There is an accumulation term. How does the concentration of compound I change over time? And then a transport term where concentration coming in and concentration leaving the system, plus a reaction term. And here I hope you start to see where all the Q and rates that we have been estimating so far will start to be very important, exactly in this expression here. Now for constant volumes, if we define the dilution rate as Q over V, we can rearrange this equation in this form, which is a little bit simpler to look at. Now, if we go for specific mass balances, we have the mass balance of the biomass, where our rate biomass is produced is, or we assume at least at first that it's produced, the rate is mu. And from the Monod-like equation and the Herbert-Pert equation, you can directly derive this expression for the biomass specific biomass growth rate under the actual conditions of your system, based on parameters that we all know how to estimate or to take from literature. Now, what is important for you to know or to realize is that while the Q is always positive, if you look at this expression, there will be a value of concentration at which your mu becomes 0. Because the consumption of your substrate for maintenance is always constant. Only the remaining fraction of substrate can be used for growth. And if this is not sufficient, then you will get a negative growth rate. And there is this concentration of minimum concentration of substrate, below which your biomass concentration will start to decay or to decrease. Based on this system of equations, we can derive and write down the differential equation on how the biomass will evolve over time in your given system, given a dilution rate, an influent biomass concentration, and all these other parameters characterizing your biomass. For the growth limiting compound, J, the evolution, the accumulation term of your compound is again a function of influent and effluent concentration, the dilution rate you impose, and the rate at which this substrate is consumed. And with the Monod term, we know what it looks like. Finally, all the other compounds will be consumed according to the rate at which the growth-limiting compound is consumed based on stoichiometry. Therefore, the rate of their consumption or production is simply given by the Herbert-Pert equation. And with this, I see you in the next video where we will be really looking into the details of this and where I hope for you to consolidate what you learned and to see it as an outlook for more complex modeling experiences.